Okay, so the next thing we're going to talk about, we're going to start with limits. And limits, glancing at a graph is the easiest way to find limits. So for example, since we're going to be dealing with logs a lot, I want to start with a graph. Sketch the graph of y equal natural log of x. So I'm assuming you know how to graph that. The graph looks like this. Assume that's a 1 right there. The graph looks like this. So if I am to say, what is the limit as x approaches infinity of natural log of x, what would you say? Well, if I glance to the right, that seems to be approaching infinity. Going up very slowly, but eventually it will reach infinity. And if I take the limit as x approaches 0 from the right, as x approaches 0 from the right, that would be approaching negative infinity. Now, this will change completely if I was to say, hey, what about the limit as x approaches infinity of absolute value of natural log of x? How about the limit as x approaches negative infinity of absolute value of natural log of x? Well, a quick sketch will really do the trick and save you a lot of pain on all of those. If I really look at the sketch of this graph, you know what? That's not what I meant. Let me put that on the bottom of it. Here. So everything matches. If I look at the graph, again, the graph gives it away. I'm taking this graph, by putting an absolute value, I'm saying now y is, by putting an absolute value right there, I'm saying that this part is going to reflect. Assume that's a 1. So the right side unaffected, but the left side now will look like this. This will reflect up there. And now, this will be infinity because I could tell it is infinity. That didn't change. However, this right here, limit as x approaches 0 from the right in this case, that would be infinity as well. Do we see that? And what if I went ahead and I said, you know what? Find me the limit as x approaches infinity of natural log of absolute value of x, the limit as x approaches 0 from the right, natural log of absolute value of x. Well, here I will go to the basic graph, which is natural log of x, putting an absolute value. So natural log of x is a graph that looks like this. The absolute value on the x will make it reflect with respect to the y. And what I'll notice, here I will get infinity. It's right there. And here I will get a negative infinity. So it makes a big difference of whether it's a function, there's an absolute value involved, or any of that. Alright? Now, a couple of things I want to get out of the way. A few things that come up later. We're not there yet, but this is the class that deals with those. Think of it as large numbers. When I say infinity, don't think of infinity as this unreachable number. Think I have a very large number and I'm adding a very large number. Wouldn't that be extremely large? What happens if I take 2 and I multiply it by a very large number? Wouldn't that be large? What if I take negative 1 and multiply that by a very large number? What if I take a very large number and I square it? Yeah. What if I take a very large number and subtract it from a very large number? This is coming up by the end of this chapter, L'Hopital's rule. For now, only this case arises. There are other cases that we're not sure what they mean. And do you notice here, as x approaches infinity, this is infinity and this is infinity? Well, here I could really use properties of logs to combine those. And that would be the limit as that would be, remember, from 5a, log limit of a function, of a composition of a function is the composition of the limits. And here, I could divide by the highest power term of the denominator. You had a whole section on that. It was called horizontal asymptote. That is limit as x approaches infinity. And something that we're going to use even after we learn about the famous L'Hopital. Anything over x will approach 0. I forgot the natural log. And when people get excited, they do amazing things. So that's natural log, and this will be a 1, and that will be a 0 in this case. So what's infinity minus infinity? In this case, it's a 0. Sometimes it's bigger, sometimes it's, it depends. We'll deal with all of these cases later on. For now, recall that we took a derivative of a natural log of x, and we got it to be 1 over x. And the antiderivative will pick an absolute value. So, I'm going to do a few problems out of the book, and this is on page 445, of course. Let's look at number 18. Here we go. Let's look at number 18. The derivative would be product rule. Derivative of the first times the second, plus the first times derivative of natural log of x is 1 over x minus 1. That would be natural log of x plus 1 minus 1. They cancel out, so I'm left with natural log of x. And if I take a derivative, and here's where you're going to reinforce the product rule, the quotient rule, the chain rule, the implicit differentiation, all of these things. When I take a derivative of a natural log, it's always 1 over whatever that is, the argument, times the derivative of this. Bring the power down, subtract 1 from the power, times the derivative of sine, which is cosine. If you clean this up, that would be twice the cosine of x over sine of x, because one of those will cancel with one of those, or the back of the book will have twice cosine of x. If I take a derivative of number 30, derivative of the top times the bottom, minus the top times derivative of the bottom, all over the bottom squared. That's the calculus. If you want to clean it up, if you really say that's 1 minus v plus v natural log of v over v into 1 minus v squared. That's what the back of the book will have. 26. By now I did too many of those. If I take a derivative of this, derivative of a square root is 1 over twice the square root times the derivative of that argument, and that will be 1 over it. And that would be, so if on the exam I say set up, do not solve, that's always the first box. For the homework, you're responsible to save everything, to simplify everything. But on the exam, I might ask you to do the calculus. 28, I'm doing that 2 different ways. First way, I'm going to show you brute force. It's kind of fun. Derivative of a square root is 1 over twice the square root. And we know from 5a that any letter they use would be a constant unless they tell me otherwise, times the quotient rule. Derivative of the top times the bottom minus the top times derivative of the denominator all over the denominator squared. And this would be a lot of fun for you to finish as a practice and get an answer. I do mean that. I'm not being sarcastic with you. This is something I really enjoy. And I have another way of doing this. I could, if I want, say, you know what? This is, I could say this is natural log of a squared minus z squared over a squared plus z squared to the 1/2. I could say this h is 1/2 natural log of a squared minus z squared, right, over a squared plus z squared. And I can even say this is 1/2 times natural log of a squared minus z squared minus natural log of a squared plus z squared. And I could say h prime is 1/2 1 over a squared minus z squared times negative 2z minus 1 over a squared plus z squared times 2z. And there it is. The beauty of logs. They do wonders for us. And I want to look at number 42 first. 42, I want to take the derivative of first things first. This thing that I see a natural log. F prime is 1 over, actually let me stick with the colors. F prime is 1 over the first argument, which is natural log of x. Now that I've done that, I'm looking at this, times 1 over the argument of the inside, times 1 over x. Don't tell me that wasn't a lot of fun. And if I look at number 40, if I take a derivative, that is 1 over x squared minus 2x times 2x minus 2. They say find the domain of f. So, okay, this is the derivative. That's calculus. Find the domain of f. Domain of f would be the argument must be bigger than 0, right? Two ways of doing this. Either you say x into x minus 2 is bigger than 0, make a table, do the testing, right? See where it's positive, negative. Or sketch a graph of this. So you know what? That's going to cross at 0 and 2. This opens up, so it looks something like that. And where's this graph positive? It's positive negative infinity to 0, union with 2 to infinity. There it is. All right. Find an equation for the tangent line. Hey, what do you know? I remember how to do that. Equations I could always play with. That is y minus y1 equal m into x minus x1. Look, I'm almost done. How fun. So how does that work? That's a number 42. I don't know why that's here. So here I would say y prime would be 1 over the argument times, and if I evaluate that at x equal 2, y prime would be 3 times 4, 12 over 8 minus 1, which is 1. There's my answer. Number 50 says find y prime given the following. So I rearrange things a bit. There's the answer. So derivative is 1 over xy times derivative of the argument 1 times y prime plus x, 1 times y plus x times y prime equal the product rule, y prime times the sine of x plus y the cosine of x. So if I cross multiply, y plus x y prime equals xy y prime the sine of x plus x y squared the cosine of x. I would get all the y primes on one side, everything else on the other side. Xy prime minus xy y prime sine of x equals negative y plus xy squared cosine of x. Since y prime is common in both, I would factor that. Y prime into x minus xy sine of x will equal negative y plus xy squared cosine of x, and y prime would be, if you factor a y out of the top, you could take the negative, you could leave it in, it doesn't matter. Actually, you could leave it as is. just that it might simplify. And if it simplifies, you need to simplify it. I'm going to factor an x out of those. And nothing simplifies, so you could leave it as is. Or you could actually factor that out. It makes no difference.